Hello, today we're going to be solving the 2017 Aime I problem 15, which states the area of the smallest equilateral triangle with one vertex on each of the sides of the right triangle with side lengths 2, 3, 5, and root 37 as shown is m root p over n, where m and n p are positive integers, m and n are relatively prime, and p is not divisible by the square of any prime. Find m plus n plus p. So we're going to solve this problem using coordinates in the complex plane. And that might seem a little unintuitive, but by looking at the problem, it does not seem very efficient to solve this by only using synthetic methods. So let's start off. I already assigned coordinates, which is good practice when you're doing these types of problems. So let's call this the origin right here is 0, 0. Let's call this length here a and b. And then we can fill in these lengths as 5 minus a and 2, 3 minus b. So now we can find the coordinate of d here, which is simply negative a, b, since we're going back a units and up b units. And now we can try to find the coordinates of e right here, which might seem a little tedious. So how are we going to do that? Well, what information in the problem is going to allow us to solve for the coordinates of e here, given these variables? Well, we know this is an equilateral triangle right here. This is equilateral. So what do we know about this angle? This is going to be a 60-degree angle. And we also know this is the origin. And that screams to us that this is just a rotation right here. This is just a 60-degree rotation. 6 degrees counterclockwise. So in fact, we can write this as a complex number to find the coordinates of e right here. So we can write this as negative a plus bi times the cis function of negative 60. And if you're not familiar with the cis function, it is just what you can multiply the what points in the complex plane by to rotate it about the origin. And we know this is equal to 1/2 minus root 3 over 2i. Root 3 over 2i. And by doing some simplification and splitting the real and imaginary parts, we get that this is simply negative a over 2 plus b root 3 over 2. This is by multiplying this negative a times this 1/2 and multiplying this bi times this negative root 3 over 2i. And now we can find the imaginary part, which is going to simply be a root 3 over 2i. Let's put this I at the end, and bi times 1/2, which is just b over 2 times I. And just like that, we found the coordinates of e by using the complex plane, which would have been much harder if we didn't have that utility. But now what? We have all these points, but we can't utilize them. We already found out that these are the same distance from each other, and that we formed an equilateral triangle by using these coordinates. So what other information are we given in this problem statement here that we can use to find the minimum value of the side length? Well, we found these lengths earlier, so what if we fill this point in? And we know this is a right triangle, so E lies on AC here. Aha! We can write the slope AC here as negative 2 3 over 5. And E lies on this, so that means CE must have the same slope, and we already have all these coordinates which will allow us to do that. So what can we do? So let's take this here, a root 3 plus b over 2 which is simply y2 minus y1, and then negative a plus b root 3 over 2 minus 5 minus a, and this is actually going to be equal to the slope here, which is equivalent to negative 2 root 3 over 5. So now let's simplify the denominator here. We have this fraction. Let's multiply both sides by 2. This will not change the value of the fraction. So this is simply equal to a root 3 plus b divided by negative a plus b root 3 minus 5 plus a. Or actually, we have to multiply everything by 2. So that's a really easy way to make a silly mistake, so make sure that you don't do that. And now we can just cross multiply 5a root 3 plus 5b is equal to, now negative, don't forget the negative. So this is 2a root 3. Or we can combine the like terms first of all. This is going to be a, so negative 2a root 3 minus 6b plus 20 root 3. And let's erase this, because now we have the equation that we desired. And now what do we have? You can combine like terms. 7a root 3 plus 11b is equal to 20 root 3. And just like that, we have a condition for a and b. But what are we going to do now? We have to find the side length, and we want to minimize the side length. So what do we know about the side length? Well, the side length here is just square root of a squared plus b squared, which you can see by this right triangle here in the Pythagorean theorem. And this screams to us the CS inequality, which states that a squared plus b squared, and then 147, which is 7 root 3 squared, plus 121, which is 121 squared. So essentially what we did here is split the coefficients and the variables together and squared them, which is what we do in the CS inequality. And this is always going to be greater than 7a root 3 plus 11b squared. Which is equal to 1200. And we know this is equivalent to 268. So then a squared plus b squared is greater than or equal to 1200 over 268, which is equal to 300 over 67. And this is in fact going to be a minimum value, because this is an inequality, and a squared plus b squared is only going to increase. So now we found out the side length here is just the square root of this. And now we wish to find the area of the triangle, which is simply s squared root 3 over 4. And we know that s squared is actually 300 over 67. Over 67 root 3 over 4, which gives us 75 root 3 over 67 is the area of the equilateral triangle, And the answer is 145. And just like that, we solved the last problem in the Aime with simple complex numbers. And that is going to be it for this problem solve. Thank you for watching.